I guess we can get started here.
Yeah, let's go ahead and get started. Today, welcome to Northeast Ohio's Cloud Security Alliance meeting for May 14th, celebrating 15 years of the Cloud Security Alliance this month. And today we have Ted Shorter presenting us on post-quantum cryptography. And he's also my boss. So be nice.
Oh,
So
be nice.
So be nice.
Is that true?
All right.
I guess maybe technically, I suppose that's true.
Some way up there, yeah.
There we go. So yeah, I'm glad to be here. And as Frank said, I was going to talk through kind of first a quick introduction to just quantum computing and post-quantum cryptography. Not super in depth, but just explain why some of this stuff actually matters in the near term. And there are some things that are actually happening and have already happened that folks really kind of need to be aware of. It's interesting. So as CTO, I wind up getting talking with a lot of our customers and our government customers and our large financial organizations, banks, insurance companies, folks like that. Are very much tuned into what's going on with especially post-quantum cryptography, as we call it. And we have conversations almost every week about that. What's interesting is if you remove the government customers and the large banks, all the rest of our customers seem to be kind of blissfully unaware of what's coming down the pipe, and some of it actually, again, happens pretty soon. So we'll talk about a lot of that, and should have maybe some time for questions as well if people are still on. I think mostly this is I think most folks are going to be watching this in recording, but so quantum computing in general, I guess the story of quantum computing maybe starts about 100 years ago. With the story of quantum mechanics. So the 1920s was about the first time that as humans, we really had the technology to start probing into not just atoms, but subatomic particles, and start to look at observations and do physics around subatomic particles. And people very quickly realized that subatomic physics works completely differently than larger object physics, and encountered some very strange properties. Things like you can have subatomic particles that actually live, or electrons that live in multiple states, and more so that can actually be where you measure them not as a probability, but they literally have no absolute position. They have a probability of where you might find them, which is just crazy. But then when you measure them, they actually take a specific state. And then this idea of entangled particles, where you can actually have two particles that actually affect each other, even when separated at very large distances, which kind of violates, it means that some sort of information or something is traveling at faster than the speed of light, or things like that, to the point that Einstein actually cited it as spooky action at a distance, and more or less, I think, used a lot of this to sort of reject a lot of the math that was starting to develop behind this, because it just didn't make sense to him. But it turns out that through experiments that people were able to run later in the 60s, 70s, 80s, and today, that this stuff really does work, and then the math works, even if it's just sort of bizarre and sort of flies against the face of reason in a lot of ways. So sort of all of this starts with the fact that in this particular case, Einstein was wrong. So that's where you start from with quantum computing. But what people realized after some time, maybe starting in about the 80s or 90s, I think the 1990s was the first time I heard the term quantum computing, is that people realized that may be possible to actually exploit some of these really strange properties to perform computations. And in doing so, by using some of these things like the multiple states piece and probabilities and so forth, that you actually may be able to perform certain computations at near instantaneous speeds, much faster than conventional computers of today. And that's been quantum computing has been this sort of theoretical research project amongst the very small elite group of folks for a very long time, but it's started to show enough progress that more and more folks really kind of believe that it might be a matter of time until quantum computing really becomes a reality. And there, for a long time, there were folks that really thought it may not be possible at all, but it's starting to look more and more like that's the case. A couple things worth pointing out. A quantum computer is not, don't think of a quantum computer as just a faster conventional computer. It works completely differently using completely different physics. And moreover, it is not Turing complete, as theoretical computer scientists would say, which means that there are certain computations that conventional computers can do that quantum computers actually can't. So basically, you know, there are certain types of computations that quantum computers will be really, really, really good at, and there are others that they will be completely awful at. And so, you know, this is sort of, you know, I think a lot of this will wind up being done with a blend of a true quantum computer and some conventional computing, kind of helping out and directing things in between. So in terms of cryptography, and I think that's where, you know, we were talking before the session, you know, most folks that are looking at quantum computing, there's a lot of amazing good things that quantum computing will be able to do. From a cryptography and PKI perspective and so forth, you know, most of the people in the circles that I run in think of it as being exclusively bad, and that's because it really does have an impact on cryptography. I guess the impact that it will have, I think, is really kind of shown here. So, to review, if you've done CISSP training or things like that, there are really three major types of cryptographic functions. There's symmetric algorithms like AES. There's secure hash functions like SHA-2, SHA-3, and there's asymmetric cryptography like RSA, ECC, and ECDSA. The first two, the symmetric algorithms and the hash functions, are mostly unaffected. If a quantum computer is able to be produced with enough strength, enough qubits, enough computing power to threaten cryptography, the way that AES works and SHA-2 and SHA-3 and the hash functions work are such that there really shouldn't be that much of an impact. They use some of these mathematical computations that quantum computers aren't good at, and so they're mostly unaffected. Unfortunately, though, the asymmetric algorithms, and by the way, pretty much all of the asymmetric algorithms that we use today, RSA and ECC, drop completely to zero, and there's no way to make them any better. You can't solve it with bigger keys. It's just they're just zero, and there's no strength from them henceforth. The real problem is that basically means that almost all of the internet effectively would be wiped out in terms of cryptographic security if that happened today. Almost all of internet security, TLS, SSH, any digital signature, that means signed code, software updates, firmware, document signing, things like SMIME, all of that is completely insecure. It's interesting, you know, Bitcoin. I got asked about Bitcoin, blockchain, that sort of thing. What's interesting with blockchains is that today the chain itself, the blockchain itself, is actually computed through hash functions. So that's would be still secure. So you'd have a very nice solid ledger. Unfortunately, all the identities of the Bitcoin and cryptocurrency wallets and the transactions, the identities that are performing the transactions on the blockchain are completely insecure. So I guess in some way we know that a quantum computer of that strength doesn't exist today because Bitcoin is still worth something. I think you might see if people start wondering where cryptocurrency is disappearing to, that might be a good sign that a nation state of some sort has been able to break RSA and ECC. So this obviously, you know, you have this massive threat, but then this kind of nebulous, when could this happen? I don't know when it's going to happen. You know, and of course, in general, as humans, have difficulty dealing with severe threats that are kind of looming very far in the distance potentially. And so, but this really does have real impacts, and I guess I'll talk about a few of them. So this chart is kind of interesting. I'll explain it in a second. This is more or less every year at this mathematics conference, they asked a group of cryptography and quantum computing experts um, the likelihood of how long it would take to have a quantum computer that can break RSA 2048, which is effectively the entire internet today. And and so they did it in sort of a heat map, right? So basically, different people. Some people think it's what's the probability within 5 years? What's the probability within 10 years? So forth. For the first time, more than half the people think it's in 15 years or less. And so, 15 years still seems like a long time, but that comes up quickly, and I'll mention I'll get to that in two different ways in a second. But this is really the first time that happened. And by the way, this happened 2 years ago, so now it's even quicker than that. So I think there used to be, like I said, people who really thought that this would never happen. I think most cryptographers really now believe that it is a matter of time. The only question is how much time. And we have a while. There's things that we have to do to be able to adjust. So NIST took note of this. So what's happened so far? So the government started seeing enough progress in the quantum computing arena to realize that they needed to do something. So starting in 2016, they actually started a competition process to develop new standards for asymmetric algorithms that are resistant to quantum cryptography, because all the ones we have today would be broken. And they do this a lot. So NIST has run the same process. They've done it for AES, they've done it for SHA-2, SHA-3. They're doing it for lots of other algorithms as they go. It's a very open process. They take submissions for algorithms from academia, from governments, from the private sector, and so forth. And then they all hammer each other's contributions and sort of go through this whole process of trying to evaluate the security in a very open and transparent process. And that's been going on for some time. In July of 2022, so now 2 years ago almost, they announced a set of finalists, which is basically to say these things have been hammered on and have stood up to the challenges, and then basically said, we're going to aim for having these actually approved as new cryptographic standards like ECC and RSA and AES and so forth in 2024. So the standards are coming. They also mentioned, I can go into this if people are interested, but there are two algorithms actually already standards that are asymmetric and are widely believed to be quantum resistant. However, they are stateful, which creates all kinds of crazy ramifications, which pretty much makes them impractical to use in the way that people are used to using asymmetric algorithms today. So by and large, most folks are kind of ignoring those algorithms, to be honest. But in 2022, NSA actually put out a directive that said that starting in 2025, we don't want to buy anything from you, especially hardware, Mr. Vendor, unless it prefers quantum resistant cryptography for its firmware updates starting in 2025. And basically even encourage people to start using these hash-based or these stateful ones, because that was the only ones around. That kind of set a lot of the hardware manufacturers scrambling, because that's really a lot to ask in a pretty short time as far as hardware, firmware design, release process, and so forth. Especially given that the stateless standards are not out yet. So as a vendor, this is really the first place where you've seen an entity say we aren't going to buy something unless it's using these new cryptographic standards. I fully expect, by the way, that will continue to happen. So once these algorithms do become standardized, and this is the way PKI and a lot of other standards happen, it starts with government saying, setting the tone of like, we're only going to buy certain things under these criteria. Then that leads into larger financial organizations and so forth that have a lot to lose if their cryptography is compromised. and then sort of flows down to the rest of the private sector. And I do expect that that will happen. I think you're going to start seeing, these standards are going to get announced, and over time you will start seeing requirements to vendors saying we need you to use these quantum resistant algorithms. We don't want to use the conventional ones, and that's going to make people switch. Really, whether a quantum computer happens or not, the standards are there, and you're going to start to see a push for adoption. I think the other point worth making is there's several things that actually push the need for that forward. One of them is that you don't have to be able to decrypt things today. If there are super sensitive pieces of information that you can mine today and then save off and decrypt later when a quantum computer is able to break that cryptography, nation states are already doing that sort of thing for particularly sensitive data that will still have value, in the future when that happens. And then finally, late last year, NIST announced a final draft for public comment, which is basically the last step in the standardization process, and now has signaled that they are going to announce the date that they gave a few weeks ago is July. So we fully expect to have in July a new set of 3 cryptographic algorithms that can effectively replace RSA and ECC as in terms of their use for asymmetric cryptography. And you're going to start see governments and so forth start to ask vendors and so forth for that use, for them to use that. So what that really means is, really whether a quantum computer ever threatens quantum or current cryptography or not, there's new algorithms that are getting standardized, and that means a lot of things are going to need to change. So if you think about things like TLS, things like PKCS11, which is the way that you talk to HSMs, things like anything that uses really cryptographic libraries, hardware security modules, TPMs, any product at all that uses cryptography in any way, which if you think about it, anything that communicates on a network uses TLS. Guess what? That uses cryptography. All of that stuff is going to have to change. Some of it's going to have to change just a little as far as being able to specify new algorithms. Some things are going to have to change a lot. Some things to point out is, I'll get to why some things are going to change a lot more than you might think. But this is really a pretty disruptive change that effectively, over time, anything that communicates on a network is going to have software updates and be able to handle the new algorithms. And that transition that organizations, that's the conversations that I'm having with the government and with large banks and so forth are around, how do we plan our transition? What do we need to focus on first? What is their strategy for that? They literally have, a team, an owner who is responsible for the roadmap through the process. And the roadmaps are getting pretty detailed. They're out talking to vendors about their support of these algorithms. And so, this stuff is coming. I think so. Some of us have been doing PKI and cryptography for a long time. We've gone through, when I started doing PKI, the MD5 hash algorithm and RSA 512 was actually perfectly acceptable. And now both of those are actually blocked for use by Windows and other operating systems by default. So we've done cryptographic algorithm changeover in the past. So there are things we can kind of learn from that, right? One of them is that the timeline sort of follows something like this, right? So standard gets adopted. So the start, that's more or less the starting line for this in many cases. The next thing that happens is the new standards need to get implemented in cryptographic libraries, OpenSSL, Bouncy Castle, which we're actually the caretakers of, hardware security modules, so forth. Those libraries then get used inside of products and operating systems, things like Windows, things like Android OS, iOS, anything that runs an operating system, any piece of software that needs to communicate, applications, so forth, need to make use of those algorithms. And so those all need to get updated. Then at some point after that update process, organizations reach a critical mass where first of all, now you can start deploying those, right? So you roll out your new version of Windows, you roll out your new version of iOS and so forth. once you get to critical mass, where as an organization, I've got, it doesn't do any good to roll out a new algorithm if I have, if the systems that I need to communicate uh, can't support that algorithm, right? So I have to get to a point where I've got critical mass in my organization. In a large enterprise with a very diverse set of devices, that can be a pretty long time. But once you get to that point, then you can roll that out and actually start to deprecate the new algorithm. I'll point out, I mentioned SHA-1 to SHA-2. Most of our customers in the PKI world they finished their transition from SHA-1 to SHA-2 in about 2016 or 17. I think most were done, but we do still have customers that are asking us to run SHA-1 based PKI for them and so forth. And that's because they've got some old legacy system that they need to be able to support. So, think about a stamping machine in a plant floor that runs Windows XP, or a CAT scan machine in a hospital that runs Windows, even Windows 7, Windows 11. Windows 11 doesn't support post-quantum algorithms because they haven't come out yet. For a lot of these things tend to have, older, some kind of OS lock-in sort of thing. Handheld scanners is another one that comes up a lot. And so if you start to think about that, and you combine that with this idea of gathering things in advance and breaking them later, 15 years really doesn't seem like that long of a time. And that's why the NSA and government is acting. That's why I think you're going to start seeing standards. I fully expect to see RFPs next year that will ask about support for quantum algorithms and all of that. So a lot of this really is, even though it seems like a distant threat, the need to act is actually starting very soon. And so, as I mentioned, like PKI passed, like it is really hard to change algorithms. We lived through, really one or two algorithmic changeovers. SHA-1 to SHA-2 took 5 to 7 years. And that was one algorithm. Now we're talking about changing over, a much broader set of things. IoT things tend to go first because they're smaller boxes. So if you control the thing that you're building and your backend that supports those things, you have more of that stack under your control. So we typically see those things move first. It's not going to be just the end entity certificates and keys. It's also your roots of trust. So literally all of your, all the public PKI roots, DigiCert, Sigtigo, and Trust, so forth, all of those folks have to create new roots. You have to, as a customer, roll out all of those new roots. If you're running your own internal PKI, you're going to need to deploy your own PKI with the new quantum resistant algorithms and roll that out to all your organizations. And of course, with all of that changeover, automation is going to be super critical. And so, there are things you can actually be doing now, even before the standards come out, and we'll get to that in a second. A couple other things worth noting. I do get asked about speed sometimes. So this is all new mathematics, or at least different mathematics than what RSA and ECC are based upon. So far, what we've seen is that the speed, the runtime of these algorithms, performing signatures, doing encrypts, decrypts, all that kind of stuff, really doesn't appear to be that much worse than RSA and ECC. And in fact, in some cases, it actually might be faster. The big difference is that the keys are larger. And so this is another reason why some of the protocols that I mentioned earlier are going to need to change. Some of the keys for the algorithms that we're talking about are 10 times bigger than RSA keys or more. So if you think about what that means to protocols, TCP/IP packets, the TCP/IP handshake is kind of based on an assumption that an RSA key is a certain size. That's now gone. There are a lot of protocols that are assuming keys are certain sizes, and you're talking about 2 megabyte keys potentially, right? So like it's going to affect databases, it's going to affect bandwidth, it's going to affect protocols. It's going to break applications that make those similar assumptions about key sizes and so forth. So that's probably one of the more disruptive changes, just from the use of, as someone who's not having to implement the algorithms, but just make use of them. Size is going to be a big issue in some cases. So as far as what you can be doing now, right? There actually are, and I'll get to that in a second, these pre-standard candidates are out. Don't use those in production because the NIST has a habit of changing the parameters of the algorithms slightly and the identifiers for those algorithms when they standardize them. So if you roll out with them today, they will effectively be orphaned, and effectively you'll be deploying something that is not the standard when the standards come out. However, it does make sense to potentially play around with the new algorithms, and there are lots of ways you can actually do that. I'll get to that in a second. But one of the big things that you can be doing today as a large organization is start with an inventory. You can't change over what you don't know you have. So start with getting an inventory of all the keys, certificates that are in use today, and start planning for a changeover. What is it going to mean to swap out my cryptography for something else, and work on automation, right? Because hopefully, your plan could include manual pieces, but if there are things that, if there's too much manual, you're just not, it's going to take too long to do. It probably makes sense to focus on the perimeter. Most likely that's where, things like the capture now, decrypt later sorts of things would happen on data going in and out of your network. That's also, by the way, a more closed system, because if everyone, kind of on that perimeter side is able to move to quantum resistant algorithms, then most of the traffic flowing over the internet itself can be using the new algorithms, even if you still have legacy stuff inside your organization that cannot use the algorithms yet. So that to me seems like a pretty good strategy. If you are a software device manufacturer, uh, definitely, one other area of focus will be on your signing, software updates, firmware updates, especially because of the NSA directive. That also makes sense. If you're Microsoft, for example, and we do have a quantum apocalypse, as they're calling it, and Windows Update, for example, has not moved over to using quantum resistant cryptography. If you can't secure your updates, then you can't secure anything, right? You can't roll out new updates. You can't. There's no backbone upon which to stand to do anything else. So it also makes sense to focus on um, software updates, firmware signing, that sort of thing if you're a vendor in that sort of space. And the other piece of advice I'd give is that if you are an IoT device manufacturer, uh, or really anyone, but focus on updatability. So I think we've seen a lot of cases. There are too many things that are still hard coded, like the we have like the customers that are still needing to do things with SHA-1. If you don't design in that ability to update your algorithms, update your keys, have ways of making these things updatable, especially if they're going to be around for a long time. If you're making durable devices, vehicles, things that you expect to have to service for a long time, that updatability is critical. And I think we've seen a lot of cases in these kind of recent algorithmic changeovers where where people would really wish that they would have done that. Um, so I think those are big pieces. And the other point that's worth making is, we've already done algorithmic changeovers. We already moved from MD5 to SHA-1. We've already moved from SHA-1 to SHA-2. We've already moved from RSA 512 to RSA 2048. Like, these transitions do keep happening. And so the work to get an inventory, to work on how you would do a changeover, to work on that updatability, those are things that are actually going to pay off for you, even if quantum computing doesn't become a threat to cryptography, or at least not a threat to cryptography during your professional career. But there are, again, it is at this point, I think by all experts, or the vast majority, just a matter of time. So it's really a case of when we're going to have to do all this work. And the sooner you start, the sooner you'll be done. So with that, I guess a couple things, a quick, why do I know as much about this, and why am I paying as much attention to all of this as I have? Because we play in the space. So Keyfactor really is all about what they now call machine identity. That means things like keys, certificates, public key infrastructure, and so forth. We are the caretakers of the open source Bouncy Castle crypto libraries. Those are free open source, probably the second most used cryptographic library to OpenSSL. We, by the way, have implemented all of the NIST candidate algorithms already. We did that last year. If you want to play around with those, download Bouncy Castle and you can go ahead and use them. Um, we're also we also have EJBCA, which is probably the second most used certificate issuance software, second to the Microsoft CA, because everybody has a Windows Server license, but actively updated and uses Bouncy Castle. So EGBCA, we had a release starting last summer that actually can issue certificates with a couple of the post-quantum algorithm candidates. And Sign Server can sign code and artifacts. That also has been updated and can sign with quantum resistant um, uh, algorithms. And then Keyfactor Command is our certificate management software that is able to do inventory of your certificates and automate the update of those certificates and roots of trust. So we very much play in this space. For our part, when those standards get adopted in July, Bouncy Castle, we expect it to be a matter of weeks before Bouncy Castle would have support for those algorithms. That will allow us, and by the way, the uh, hundreds or even thousands of folks who make use of Bouncy Castle throughout the world will also be able to make use of those algorithms in their own products and systems. So we'll start there, and then our updates for support for those new algorithms will move to EJBCA and then Sign Server and Command for management. So, our goal is to help lead our customers through a quantum transition. We very much want to make sure that we aren't the reason why you can't as well, and trying to make sure that again those algorithms are available, implemented, and able to be used by all of your vendors that make use of at least that make use of Bouncy Castle. A couple other things that I can mention. If you want to play around with this stuff more, we actually do have something we're calling the PQC Lab. If you go to keyfactor.com, Post Quantum Cryptography Lab, you can play around with it. We actually update this information relatively frequently as new components and new capabilities come out. But you can play with the quantum algorithms and get a lot more information if you want to familiarize yourself with some of those things. So with that, I think that's all I really had to share this evening. But certainly, if there are any questions from folks that are still on, I'd be happy to answer those.
Hi, Ted. This is Frank. Yeah, I actually have a question. I hadn't thought about the disk required for PQC. So
Yep.
we're looking at like IoT devices that we have
Yep.
today
Yep.
that are designed to not have a lot of disk, not a lot of space.
Yeah.
So manufacturers have to start. Fortunately, disk space has shrunk
Yes.
and gotten cheaper, but we still have to update those devices with
Yeah.
this.
Well, yeah, there. I mean, obviously, no matter even with Moore's law and so forth, there will always be constrained devices, right? Because people keep, the small devices keep getting more and more powerful, but people keep making newer, smaller, more constrained devices. So NIST recognizes that as well. So there actually is standards work going on for a quantum resistant algorithms more with things like IoT in mind or constrained devices in mind, because the storage really could be an issue. If you think about it, even if it's a super constrained device, if you want to verify a signed firmware update on an IoT device, you need to store the public key that you're validating that against. And so like that's right there, you got a problem if the key is too large to store in your memory. So they are working on there's going to be a separate standard this is working on. It won't be one of the ones that's announced as a standard in July, but that is coming because they see the same that same constraint. Super good question, though. The other thing that's weird, I guess, while I mention, for those of you who played around with asymmetric cryptography at all, or even digital certificates and so forth, today RSA and ECC kind of work on this thing. The public key is a certain size, and then they can encrypt things in that size, right? So that like the key is this big, and a signature performed by that algorithm is about the same size, and all of the things are, the key, the private key, the public key, and a signature or encryption performed by that are about the same size. That property also kind of goes away with some of these algorithms. So there are some cases where the signature might be really, really small, but the key is really big, or vice versa, depending on what some of the algorithms are, because they use completely different math. So there are just strange things like that too, where you might have the key is small, but the signature is big, or things like that too.
So is this is doing something like a DPOD, data protection on demand,
Yeah. Yep.
with Thycotis or Tails? Is this where those can be leveraged as a strength to get you through?
Well, yeah.
resistance?
So DPOD is a Talus product. I will say as well. The other thing that's been happening, I mentioned governments and large financial organizations. The other people that are paying a lot of attention to this and have been for a long time are the cryptography and HSM manufacturers. So we've actually been doing interop testing with almost all of the major HSM vendors, including Talus, but also all the other ones as well, to try to make sure that we can prepare ourselves as much as possible. Those of you that are old enough to be around in the early days of the internet, there were things like, the late 90s, early 2000s, where, like the first, a certificate would work with Netscape, but not with Internet Explorer 1, things like, I'm going way back, right? But the literal dawn of the internet, there were, these kind of application incompatibilities and that kind of stuff. What I've seen so far is a lot of the vendors who are working on this stuff really are trying to get out in front of this, and a lot of interop testing has actually been going on already. And most, if I'd be hesitant to say all, because I'm hesitant to speak for all the HSM vendors, but most of the ones that I know of that I've talked to, whether it's Talus or Encipher or Udemako or so forth, their plans for implementing the post-quantum algorithms uh, uh, are such that should be doable entirely in firmware. So it won't require a new HSM hardware. Now you need to check with your HSM vendor to make sure that's true in all cases. But for the most part, their starting line as an HSM vendor is to get that stuff, get the algorithms implemented in their firmware, get the firmware updated, and then of course now you got to get that. If you have a FIPS requirement, you're gonna have to get that through FIPS, which by the way is taking an extra long time right now. There's a whole separate thing going on with trying to get even non-cryptographic or PQC related things through FIPS certifications. But in terms of support for the algorithms, I do think that should come from the HSM vendors still in this year, like 2024. I think most of them plan to have that out by the end of this year, even with the standards announced in July.
Okay.
Cool. Anything else? I guess if you have more questions, LinkedIn/Ted Shorter, feel free to shoot me something there too. Happy to answer other questions that come up. If you think of something later.
Sure. Lisa, you've unmuted.
I was going to say, I don't have a question, but excellent presentation, and so nice to talk to you again, Ted.
Yeah, Lisa, good to talk to you as well. It's been a long time. It's Bruce Zabo was on from Microsoft earlier. Also a blast from the past. So it's a small world, I guess.
Yeah.
So
yeah. This was fascinating. This was really great.
Awesome.
I learned a lot from it. Thank you so much.
I'm really glad to hear that. Glad you enjoyed it.
Yep.
Thank you.
All right.
So cool.
If there aren't any other questions, I think we will adjourn.
Yep.
Great. Thanks, everybody.
Thank you very much, Ted.
Bye-bye.
Bye-bye.
You're welcome. Bye-bye.